Heisenberg's uncertainty principle states that you cannot know precisely the position and the momentum of a particle at a given time. Off-ball principle states that as protons are added to the nucleus, electrons are going to be added to the orbitals at the lowest energy first. So off-ball is going to have to enter lowest energy. So first it goes to the 1s, then the 2s, and so on. Hund's rule says that electrons do not pair up until they have to. So if you have electrons entering the 3p, they're going to put one in each orbital since they're equal in energy, and then you can start putting them in the same orbital paired up. Pauli's exclusion principle states that electrons must have opposite spins. So when those two electrons go in the 3p, they have to have opposite spins because electrons are negative. They don't want to be next to each other. So having opposite spins is going to minimize that repulsion. Valence electrons are the electrons in the outermost principal quantum level, and they're usually only considered s and p orbitals. When writing electron configurations, you may recall this diagram from first year chemistry. The alkali metals and alkaline earth are the s block, so the period number is the same as which s. So if you're in the 5th period, you're in the 5s. The 7th period, you're in the 7s. The p's are over here. They're also the same as the period number. So 2nd period is 2p. The d's are the transition metals, so they're all in the middle. And they're the period number -1. So if this is the 4th period, this is the 3rd d. If this is the 7th period, this is 6d. And finally, the F's are the intertransition metals. They're at the bottom. If you look at the numbering on the periodic table, we go 6s1, 6s2, 5d1, and then 4f1. So follow the atomic numbers at the bottom. A lot of times people forget about these F's because they aren't paying attention to the atomic numbers. And the F's are 2 minus the period number. So for instance, sulfur is located here. So if I was reading its electron configuration, I'm going to read it like a book, and I'm going to go through the 1s first. So I go through the 1s, and there was 2 electrons in that. 1s1, 1s2. Then 2s. I go all the way through it. So 2s2, the s's can hold 2. Then I'm going to go to 2p, and the p's can hold 1, 2, 3, 4, 5, 6. So 2p6. Then I'm going to go through the 3s, so 3s2. And the 3p, I'm going to go 1, 2, 3, 4. And I need to stop at 3p4 because that's sulfur's element box. You can also double check yourself by adding these numbers on the top. 4 plus 2 is 6, plus 6 is 12, 14, 16. 16 is sulfur's atomic number, so we're good. You will not be given a chart like this on the test. You'll just have your blank periodic table, so make sure that you can find these groups on the periodic table. So one more together, let's do cadmium. So cadmium is right here. So we would go through the 1s, then the 2s, then the 2p, then the 3s, then the 3p, then the 4s, the 3d, and D can hold 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 3d10, then the 4p, then the 5s, and finally 4d, and I'm going to stop at cadmium, which is 4d10. Go ahead and pause the video and do nitrogen on your own. So nitrogen was there, so you should have had 1s2, 2s2, 2p, 1, 2, 3. For our next one, we have a charge. Sometimes it's easier to write the configuration for the atom and then figure out what the ion would be. So write the configuration for sodium, ignoring the +1. So write the configuration for sodium, restart when you have sodium's configuration. So you should have had 1s2, 2s2, 2p6, 3s1. Now we need to pay attention to that +1 charge. Since it's a +1, that means we're going to lose 1 electron. We're always going to lose it from the highest energy level. So the 3s is our biggest number, so that's our valence electron. So we're going to lose this one. Notice now we have the configuration, the same configuration as neon. Elements gain and lose electrons to generally be like noble gases, unless they're a transition metal or some other exceptions. So sodium, had I thought it meant it gained an electron, then that would have the same configuration as magnesium. And sodium is not going to gain an electron to fill its 3s, it wants to have a full outer shell. Now it has 8 in its outer shell. So that makes it stable. Go ahead and write the configuration for fluorine, restarting when you have your answer. Again, you can ignore the negative to start with and then figure it out from there. So fluorine, you should have had 1s2, 2s2, 2p5. But since fluorine is a negative ion, that means it's going to gain an electron. So it's going to put that extra electron in its p, again giving it 8 valence electrons, or the same configuration as neon. So sodium ion and fluorine ion have the same electron configuration. For F is going to be a little bit trickier. So on nickel, again, just like before, ignore that +3. Go ahead and pause the video and write your configuration for nickel. So nickel's a transition metal. I have my 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 8. But with nickel, it has a +3 charge. This one people miss all the time on the AP tests and on regular unit exams. Remember that when we had sodium, we said that positive ions are always going to lose them from the highest number or the farthest from the nucleus. We have the first energy level, we have the second energy level, we have the third energy level, and we have the fourth energy level. So the fourth energy level is the farthest from the nucleus, so those are going to be the ones that I lose first. But that was only 2 electrons. I need to lose 3. So now I can start taking them from the 3D. I would lose all of my 3D, then my 3P, and then my 3S. But I have to lose my outer energy levels first. Then you can rewrite it into that. Okay, go ahead and pause the video and do G on your own. So for zinc ion, you should have had 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Since it was a +2, I'm going to lose those from the 4s, and I'm left with that. For the next one, P -3, if it's a negative, you don't have to write the atom and then do the ion if you don't want to. So here's phosphorus. Since it's a -3, it should be gaining 3, so it gains 1, 2, 3. It should again have the same configuration as a noble gas if it's a negative ion. Only the positive ions are going to have that weird where you may not gain or lose, or gain or lose the very, very last one. So for P, we just need to write the configuration for argon. And finally, pause the video and write your configuration for iron 2 ion. So your configuration should be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6. But since it was a plus 2, I'm going to lose that 4s and just be left with 3d6. These say write the state kernel configuration, or sometimes noble gas configuration, or shorthand. So to write shorthand, you're going to find the element. So hafnium is here. So you're going to find the noble gas that comes before it. So follow it back from atomic numbers. So I'm looking at this noble gas, which is xenon. Only a noble gas can go in brackets because it's basically saying hafnium has the same electron configuration as xenon plus, and then I start reading. So 6s2. Remember, be careful with those atomic numbers. Technically, I have 5d1. Then I'm going to go all the way through the 4f's. So 4f14 if you count across. And then I go back to the 5d, so 5d1 again. You could write it this way, or you could say, I'm going to come back to the 5d's. So you could say 6s2, let me go ahead and do all my 4f's, and then I have 1, 2 in the 5d. Notice regardless, I have 2 in the 5d, whether they be separated or together. So whichever way you want to write it, on the keys, I'll be writing it like that most of the time. One more together. So radium is here. So I find the noble gas that comes before radium, which is right here, or Rn. And then I start reading. All I need to go to is right here, so 7s2. Go ahead and pause the video and try lead, HO, and TC on your own. So for lead, you should have gotten xenon. 6s2, 4f14, 5d10, 6p2, since lead is right there. Make sure that you have those f's in there. Remember that you could have also said 5d1 and 5d9, as long as you have your 10 d's and your 14 f's. HO was number 67, so you should have had xenon, 6s2, 5d1, 4f10. Because you're in the f's, we don't go back to the d's, so we have to have just one of the d's, and then we have 10 f's. And then TC was number 43. You should have had krypton, 5s2, 4d5. Notice when I'm writing the electron configurations, there's no commas between them. That's going to be incorrect. And make sure that your exponents are exponents. They're not all in the same line. So pause the video and figure out which element this represents. So if you said aluminum, you're correct. But you may look at it and say, that's not aluminum's electron configuration. So this is what we refer to as an excited state. it skips something. It goes 1s, then 2s, then 2p, but there's no 3s. You can always figure out what element it is, though, by adding these up. We have 10 plus 3 is 13, which is the number of electrons in aluminum. You wouldn't have to write an excited state electron configuration, but given one, you should be able to figure out which element it is, and you should be able to tell that it's an excited state because something was skipped. Make sure that you write that down in your notes, what an excited state is and how to figure it out. Which element has this electron configuration? Go ahead and pause the video and restart when you have an answer. So you should have said SM. You can figure it out the same way. Xenon has 54, 56, 57, 58, 59, 60, 61, 62. 62 electrons corresponds to, at the bottom, in the F's, SM. This one's a little bit trickier because it says which +2 ion has this electron configuration. Go ahead and pause the video and try to figure it out. So first, I would say look at 1s2, 2s2, 2p6, and that corresponds to neon. So then I would say, well, who's a +2 ion that would have the same configuration as neon? Well, magnesium, if it loses 2 electrons, it would have the same configuration as neon, so it must be Mg+2. If it said a -2 ion, then it'd be oxygen. -1, fluorine. +1, sodium. If it was a neutral atom, then it would have been neon. Another way you could have done it was say that this has 10 electrons, and if it's a +2, it lost 2 electrons, which means it must have had 12 electrons before it lost those 2, which corresponds to magnesium. So go ahead and pause the video and try this one. Restart when you have an answer. So this one was just like the last one. It had the same configuration. So a -3 ion would be nitrogen. I have 10 electrons, but if it's a -3, that meant I gained 3 electrons, so I technically only had 7 electrons to begin with, which is the same as nitrogen. This one, it says showing only the valence electrons. Remember, valence electrons are going to be your outer electrons, so your outer SMP. So I would suggest writing your shorthand electron configuration and then writing the valence electrons. So what that means is if I wrote the configuration for lead, we did that a few minutes ago on the shorthand. We had xenon and then 6s2, 4f14, 5d10, 6p2. So your valence electrons are your outer electrons. Those are the ones that you would be losing if it lost electrons. Rewriting it, showing only your valence electrons, would look like so. Notice I don't have my noble gas in it because this is not a shorthand configuration. It's just showing its valence electrons. Its valence electrons are in the 6s and the 6p. Go ahead and pause the video and figure out what the most likely charge of that electron configuration is. So if we were to look at this one, it has 3p3, which means it needs to gain 3 electrons to fill that 3p. Its 2 options is either gain 3 electrons or lose 5 electrons. Well, it's going to be easier to gain 3 than to lose 5. So if it gains 3 electrons, it would have a -3 charge. can pause the video and answer this one. So if you look at the answer choices, they all have oxygen. So I'm trying to replace silicon. Elements that are in the same column have similar properties, or the same group have similar properties. So I'm going to try to find an element that's in the same group as silicon, or the same family. Of the elements given, the only one that's in the same family as silicon is tin. So tin 4 oxide would be the best replacement for silicon dioxide. Each orbital has different shapes. The s orbital is going to be spherical in shape. It's going to get larger for every increase in energy level. N is energy level. So the first energy level, second energy level, third energy level. And then nodes are areas of zero probability of finding an electron. So we have 1 shell, 2 shells, 3 shells. You don't have to know the shapes of the different orbitals, but P is a dumbbell shape and there's 3 different orientations. That's why the P has 3 orbitals. The D has 5 different orientations around the axes. It has a clover shape for the most part. And since it has 5 orientations, that's why we always draw 5 orbitals when we're dealing with it. And the F's have 7. They just have a complex shape. Within an energy level, S always has the lowest energy, F always has the largest energy. So 6S is lower in energy than 4P. Or 3P is greater in energy than 3S. Because these have the same energy level or same number in front, we just say S is lowest in energy, F is highest in energy. But if you had 4F versus 5S, here's the 4F and here's the 5S. You would come to the 4F later, so 4F is higher in energy than 5S. Because remember, off-ball principle says that electrons enter lowest energy first. Since it enters the 5S first, 5S must be lower in energy than 4F. And finally, para and diamagnetic. Paramagnetic means that you have at least 1 unpaired electron. And so if it's paramagnetic, it's going to be weakly attracted to a magnet. Diamagnetic, all the electrons are paired, and they're going to be slightly repelled by the magnet. So to figure out how many unpaired electrons an element has, you need to look at where it's at on the periodic table. So there's carbon. You need to say, is it in the S, the P, the D, or the F? It's in the P, and it's in 2p2. So then I would draw the P orbital. Remember that the S has 1 orbital, the P's have 3, the D's have 5, and the F's have 7. It's the number of electrons it holds divided by 2. So I'm going to have my 3 2p orbitals. And then I start filling it. Remember that Hun says that electrons don't pair up until they have to. So I'm going to have 1 in this orbital and 1 in that orbital. So I have 2 unpaired electrons. Since I have any number of unpaired electrons, it has to be paramagnetic. Okay, one more, helium. Helium's located here. It would be 1s2 is where it ends. Well, it's an S, so S only gets 1 line. And it has 2 electrons, so 1 up, 1 down. So it has no unpaired electrons. Therefore, it must be diamagnetic. I'm going to pause the video and try zinc and arsenic on your own. Restart when you have them done. So zinc was 3d10. So in the 3D, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So no unpaired electrons, diamagnetic. And then arsenic ends in 3p3 or 4p3. So 3 unpaired electrons, so that must be para as well. The only way it's going to be diamagnetic is if it ends in S2, D10, or P6. If it's in one of those groups, then it's going to be diamagnetic. All the others are going to be paramagnetic.